Determine the radius of convergence of this power series here, which is starts with n equals 1 up to infinity, n factorial x to the n over n cubed. So it is a power series, and I can see its center is 0. And we're not interested in the center, we're interested in the radius. So how do we go about finding the radius of convergence? Okay. So if we picture sort of a number line centered around 0, okay, there are some values where it converges and others where it diverges, and there's sort of a divide. Where it diverges further away, it converges closer. Okay. And, well, we're not particularly interested in what happens at these endpoints here. We're just sort of interested in how far away is this cutoff, where it's divergence, convergence, divergence. So a great tool for finding the radius of convergence is the ratio test. Or another great tool is the root test. Okay. Now, since we've got n factorials, I'm going to use the ratio test. So we'll use, and since x's could be anything, we'll use the absolute ratio test. Okay. So we're going to leave this x in here, and then we're going to do a bunch of work. And then we know when rho is less than 1, we get convergence. And when rho is greater than 1, we get divergence. And that should lead to something like, for example, x greater than 3 diverge, x, well, absolute values, but absolute value of x less than 3 converge. Something like that. I don't think that's necessarily what we're going to get, but then that would show us this cutoff at 3 and minus 3. Anything further away diverges, anything closer converges, and then we'd see, oh, 3 must be the radius of convergence. So that's the plan. So it's n factorial, so n plus 1 factorial, x to the n plus 1, over, I think it was cube? Yes, n plus 1 cubed. All over, and then n factorial x to the n over n cubed. Now the factorials and the cubes are all going to be positive, because eventually the n values are all positive. So we can sort of leave them alone. We can also invert and multiply, but we don't know about x, so we're going to have absolute value of x hanging around. Which is good, because eventually we want something like that. Okay, so invert and multiply, so n factorial, absolute value of x to the n. Okay. Now we can write the n plus 1 factorial as n plus 1 times n factorial. We can write the x to the, well, absolute value of x to the n plus 1 as absolute value of x to the n times absolute value of x. And we see that a few things are going to cancel out. Oops, this shouldn't be factorial. It should be... No, yeah, that one's the factorial. The cube's already on top. The factorials cancel out. Okay. So we're left with n plus 1 times absolute value of x for n plus 1 cubed times n cubed. Now, the absolute value of x, I'm going to bring that outside because it has no n's in it. It's constant. I can also cancel out one of the n plus 1s. So we're looking now for the limit, as n tends to infinity, of the absolute n to the power of 3 over n plus 1 squared, which I suppose we could rewrite. And although now I'm thinking ahead, I actually am not allowed to take the absolute value of x out unless you know that the limit does exist. So let's just separate it off for a moment, because I was thinking ahead, and actually the limits aren't going to exist here. Well, except for one. Okay. So we get n cubed. I'm going to say n squared plus 2n plus 1. Okay. Okay? Now you might say, well, as n gets bigger, n cubed is going to get much larger than n squared on the bottom is. So this is going to diverge off to infinity. But if you wanted to, you could make it a bit more precise. Okay, divide by the highest power of n. So we got 1 over n plus 2 over n squared plus 1 over n cubed. Okay. The bottom here is going to 0 while the top is at 1. Okay. So this does not exist. Except when? Okay. How can the bottom not go to 0? Well, it does. But if the absolute value of x is 0, then none of this matters because you're just doing the limit of 0. And this kind of tracks because we know that power series always converge at their center. Okay? But other than that, other than the situation where the absolute value of x is 0, which just corresponds to x being equal to 0, this will not exist. Okay? So we could say for x equals 0, now we can be a bit more precise than does not exist, because I want the absolute ratio test to apply. So we'll say, so it actually tends to infinity, because it's getting very, very small, and a constant number divided by a small number should get very, very big. So first I'm going to say we see that the value of rho is 0, if x is 0, and infinity otherwise. Okay? Now, if rho is less than 1, we know we get convergence. If rho is greater than 1, or if it's infinity, we get divergence. So our power series diverges for any value of x not equal to 0. If we imagine our number line, we just get convergence at 0 and divergence everywhere. And this corresponds to a radius of convergence, you might say ROC, equal to 0. Okay? When you see that, you are saying my power series only converges at its center. And that's true in this case. So there we go. Radius is 0.